Hello everyone, welcome to the lecture series on Foundations of Deep Learning, Concepts and Applications. In the last session, we had started with CNN architecture, where you have first seen what is the inspiration for building the CNN, which is a human visual system. And then we have seen how it starts extracting the features, low level features, and gradually it goes to extracting the high level. So, from edges to shapes, and from shapes it goes to objects. Then we have seen what are the key building blocks of CNN. We have seen that we have a convolutional layer, we have a ReLU, then we have a pooling layer, fully connected layer, and we have understood how convolutional layer works, and then we have seen what is the role of a kernel and how kernel will slide over the input to produce the feature maps. And we have also explored some math behind the 2D convolutional. We have seen what is padding, and in the padding the two important concepts that is valid and same. The meaning of valid is where there is no padding that is applied, and the same we are applying padding, so that we can retain the shape of the input. Whatever is the feature map size, that will be same as the input size if we apply padding. And the main reason why we have to go for padding is we can preserve the border information. We have also seen a concept called as stride, where the stride can be 1, 2, it is an hyperparameter. Basically this will control how the filter has to move over the input, and different size of the stride will have a different effect on the feature map size. This is all what we have seen in the previous session, which where you have understood about the convolutional layer applied on grayscale or on binary images. Today let us explore how convolution works on RGB images. When you say RGB, we will have 3 channels here. So, how convolution works on RGB with 3 channels. Once we complete this, we will learn the further layers of CNN, where the next component we will see what is the role of activation function ReLU in CNN. We will understand the pooling layer, then we will go into flatten layer. And towards the end we will observe how these layers connect to a fully connected layer in deep CNN architectures. So, this is all what you will be studying in today's session. So, let us get started. So, this is what is how a convolution is applied on RGB images. When you look into this image, it is an colored image, it is an RGB. So, whenever you say it is a colored image, it is a combination of red, green and blue. This we have seen in our introductory session itself. So, when you look into, we know that an image is a matrix representation. For a system, it is a matrix representation which will have a collection of pixels or a grid of pixel values. If that is the case, we will have one matrix for red image, we will have one matrix for green, and we will have one matrix for blue. Since there are 3 matrices, therefore, we say the number of channels for RGB is 3. Okay. That is, those 3 matrices is what you are seeing here. We have one matrix for red, green and blue. So, this is a combination of this is a matrix representation for an RGB image. Now, when you look into this image, how do we read it? Any image will have a dimension. It will have a width and it will have an height and it will have a width. So, when you say it is height is 6 and width is 6 here. So, that is what is the meaning of 6 into 6, 6 cross 6. And what exactly is 3? There are 3 such channels, 3 such matrix. One is for red, green and blue. Therefore, for an RGB image, the input dimension will be, if you consider this example, the input dimension is 6 cross 6 cross 3, where 6 is the height, 6 is the width, and this 3 is the number of channels. Okay. So, this is how you represent an image in a matrix form. But what we are discussing is the convolution operation. So, what we have understood about the convolution, we require an image in a matrix form. Yes, we have an image in the matrix form, and we require a kernel. What is the role of a kernel? Kernel will go through the entire image, and then it will perform a convolution operation and produce a feature map, correct. So, if that is the case, we require a kernel. Now, what is the difference between what we have seen previously and here? Now, the kernel that we are taking is applied on an RGB image. So, RGB is having 3 channels. If it is having 3 channels, so the kernel that we consider here should also have the same number of channels. So, since here the channel is 3, here also we have to consider 3 such kernels. That is the reason this size can be anything. But here this channel should match the input size. Here, since the input is having 3 channels, the number of kernels also here should have 3 channels. This is one basic difference between what we have seen in the previous grayscale and then the RGB. Okay. If that is the case, then how does the convolution operation works? So, you will be applying this kernel, whatever the kernel that you have defined, onto this input image, and we get the feature map. So, what is the size of the feature map? How is that we calculate the feature map? The formula will remain the same, and the formula here is n minus f plus 1, and of course, you should know there is an stride divided by s. Since the stride what we are considering is 1, so we are not taking the denominator part. So, n minus f plus 1. What is n? N is an input which is 6, and f is a filter which is 3 cross 3 plus 1. So, 6 minus 3 plus 1 we get to 4. Similar way, this is a height and this is width. So, 6 minus 3 plus 1. So, when for this particular input image, when we apply this kernel, we are going to get this feature map. And what is the size of the feature map? The size of the feature map is 4 cross 4. And how are we calculating? We are calculating using this particular formula. Now, let us take one numerical example and understand how exactly the convolution operation takes place in RGB. So, if you see here, this is what is an we can say it is an R, G and B. So, we have an image with 3 matrix. Okay. Now, what is that we have seen in the previous slide? Because there are 3 such channels, we need to consider an kernel of whatever may be the size, but into 3. Why it is into 3? Because there are 3 such channels at an input, which is R, G and B. Now, what is this size we are defining here? The size that we are defining is 3 cross 3. So, that is the reason this is the first 3 cross 3, this is the second 3 cross 3 and this is the third 3 cross 3. So, therefore, we are taking 3 cross 3, but 3 such channels, 3 such kernels. So, these are the 3 different kernels that we are considering. Okay. How does the kernel works? It is exactly same what you have seen so far. Now, since it is 3 cross 3, it will be applied on 3 cross 3 part of input matrix. So, what is input? It is going to be applied on this 3 cross 3. Okay. So, what operation we are going to perform? We are going to perform the convolution operation. What is convolution operation? You will first perform multiplication and then you will do a summation. So, how is that you will do? Element wise multiplication. So, it is I am just showing for one example, the same is been applied throughout. So, it is 9 into 1. So, this 9 into 1 plus we have the second element 9 into 1. Then we have a third element 8 into 1 because it is an element wise multiplication. Then we have 0 into 0, 9 into 1, 0 into 1. Similar way we have 6 into minus 1, 7 into minus 1, 9 into minus 1. So, once we take all of these, we will be doing the summation of it. So, the summation result what we got is 13. So, next what is the next step we will do? We will apply slide. When we apply slide, this is the next matrix that we are going to consider. This will be the next matrix, and once again we perform a convolution operation using this kernel and we get the next value here, and likewise you will be repeating for this entire step. So, once you repeat, you are going to get these values. So, let me clear this so that you can able to visualize it properly. Likewise, this is one operation. The second what we are going to do is we take the second component, that is a green component, and then we take the second kernel. We have 3 cross 3 such kernels, right. So, now what we are considering is we are taking this kernel. So, once again you repeat the same operation. First it is applied on 3 cross 3, we perform a convolution operation and we get this value, and then we do a slide. So, when we do a slide and when we repeat this entire, we get these values. Likewise, you repeat it for B component also, and then we get these values. So, first initially you will take this part of a matrix, you perform convolution and you get minus 3, and you repeat this for this entire, we are going to get this. Now, ultimately we are what exactly operation we are doing? We are doing a convolution operation on an RGB image. So, from the previous slide we have seen that when you go back, so when on this input image, when you apply a kernel, we are getting a feature map. We are getting this one feature map. Why did we get only one feature map? Because we have used only one set of kernel. So, it is only one kernel, right, what we are considering. It is not, do not consider it as 3 different, no, it is one kernel only, but it is having 3 channels. So, here we are getting one feature map. Then you can ask, ma'am, here we have got 3 such. No, ultimately what we will do, we will perform the addition of respective element. So, the 13 plus 11 plus minus 3. So, 13 plus 11 minus 3, we get 21. We are going to add each of these elements. Similar way, rest of these elements will be added and then you get this. The same what you have seen numerically, graphically you can visualize here. So, this is this entire whatever you are seeing the kernel, if you consider like this as one set of, this entire is applied on this. Then you are performing an point by element wise multiplication and summation, and then you are going to get a value here. Then what you will do, you will apply stride. When you apply stride, you get something like this. Then you are considering the next part, and that again you will multiply it with the elements. The yellow part what you are seeing here is an kernel and its respective the elements of the images. So, you will again perform a convolution and you get this value, and you will stride, you get this value, and so on. You will repeat this entire and then you get the last value here. So, this is how the convolution operation is performed on RGB images. I hope it is clear. The only difference is earlier we had at an input we had the channel 1. So, because of this, whatever the kernel that you had considered only 1, but here the channel is 3. Therefore, the kernel also you should consider with the channel 3. So, this size can be anything, but this has to match with this input, and you will perform a same element wise, but now this time time you will be getting 3 such values. Then you will internally do addition and finally you will place the value here. This is how you will perform the convolution for an RGB. Now, what the same concept again, the same whatever is this kernel that you have considered, if you repeat this any number of times, ultimately the values in this feature map will remain the same. Then whatever the features that you have extracted, again and again you will be extracting the same features. So, how do you avoid it? Definitely we have to consider more such kernels. So, what we are doing, let us assume if you take this input and on this input if you apply this kernel, you are getting this feature map. Now, I want more such features to be extracted. I cannot use the same kernel again, because if you use the same kernel, same thing again and again you are extracting. So, what you will do, you will now take a different kernel, you will take a different one. Again this kernel when it is applied onto this particular input image, we are going to get this feature map. Okay. Now, how many such feature maps you will obtain, that always depends on how many such kernels. If you again apply one more, let us assume there is one more such kernel, definitely you will get the next feature map. You have one more kernel that you are placing, definitely you will get the next feature map here. So, how many such feature maps that you are getting, since here there are 2 such kernels that you have taken. So, therefore, you are going to get, this is the size of this is the output that you are going to get. So, this is the first feature map applied on this kernel, this is the second feature map applied on this kernel. Therefore, the output is 2 such feature maps. This is the first one, this is the second, 2 such feature maps is this. What we call this? We call it as an output volume. Right. Now, let us see what is the math behind, how many such we are going to get. So, definitely the output dimension formula is given by this n minus f plus 1, this is the output size. Now, we are not dealing with, this is the size we have seen, but what we are dealing is with the multiple filters and multiple inputs, multiple input channels. So, when this is the constraint, the formula will have a slight difference. What is that formula? So, the formula here is, since there are multiple filters and multiple input channels, therefore, the representation what we are going to give is n cross n, that is the input, into NC. NC stands for number of channels at an input. Then we have f cross f, which is at a kernel, and the number of channels at the kernel, which is given by the formula n minus f plus 1, which is for height, n minus f plus 1 for width, into this nf is number of such filters we have considered. So, let us take one example and then understand here. So, this is the formula n minus f plus 1 into n minus f plus 1, and this nf is the number of such filters. Okay. If you consider the same example, so what is n here? N is 6. So, and filter size is 3 cross 3. So, n minus f is 3 plus 1. This is for height, and what is for width here? Again n minus f plus 1, 6 minus 3 plus 1. So, what is that we are getting? We are getting 4 cross 4. That is what is this 4 cross 4 we have got. Okay. Then what is this 2? This 2 is NF. What is NF? Number of such filters that we have considered. How many such filters we have considered? This is the first filter, this is the second filter that we have considered. Therefore, the output size or the representation feature map output volume is 4 cross 4 into 2. What is, how is that we have obtained? We have obtained with this particular formula. I hope the small math behind RGB is clear to you. So, this is how the convolution layer is performed. We have seen so far how convolution layer is performed on grayscale image, how convolution is performed on RGB. So, with this we have completed the convolutional layer. So, before we go, a quick revision. What is convolution operation? It is an element wise multiplication and summation. If at all, and what is the ultimate aim? The ultimate aim is to extract the features, and the features it extracts we call it as feature maps. For that, what all things are required? We require a kernel which acts as an eye, which will go through the entire image, and it performs a convolution. Where if it has to go through the entire image, how you move the eye, similar way we need to move the kernel. So, in order to move the kernel, we require a concept called stride. Stride will help to move the kernel. Now, since here we have 6 cross 6 which has reduced to 4 cross 4, which means some border information is lost. In order to avoid that, we apply padding. So, here also the concept will remain the same. We will have one layer of padding applied to R, G and B. So, it is the same concept that is being carried out even for an RGB. With this, let us now enter into the second component of CNN, which is an activation layer. And here, what is the activation function that we use? We use ReLU. So, what does ReLU stands for? It is a rectified linear unit. Okay. What is the role of ReLU here? The role of ReLU is, now when we perform a convolution operation, this is just an example image that you are seeing on the screen here. Let us assume this is the output. This is the output what we have got from the convolution layer. From the previous layer we got this output, which is a feature map. Now, what will be the size of this feature map? Either the size will be same as input if you use padding. If you doesn't use padding, there is a slight reduction in the output in the feature map size. Okay. Whatever the values that you have got, those values will be the extracted features value. Okay. Now, if you look into, we have some values here. So, now when this output what we have obtained from the previous convolution operation, when we pass it to a ReLU, now if you look into, this is the values that you get. If you see here, 1 is retained as 1, 14 is 14, but when you take minus 9, we got it as 0. So, what exactly ReLU is doing? Every negative value you are from the image, you are replacing it with zeros. So, that is the role of ReLU. It is converting every of the negative value to zeros here, and it will also introduce the non-linearity. We will understand that, and let us take this with an example. Let us assume this is one feature map which is extracted from the convolution operation. And what feature map that we are showing? We are again shifting back to an grayscale only. Let us assume this is one feature map which is being extracted, and if you look into the size here is 7 cross 7. 1, 2, 3, 4, 5, 6, 7, 7 cross 7 is the size here. Now, what is the role of, and this is a feature map by doing a convolution operation. Now, what is ReLU layer? We take the first value, pass it to ReLU. What is the role, what is the formula, mathematical formula? It is a max of 0 comma x, x is 0.77. Now, when you look into what is the maximum value between 0 and 0.77, what is maximum among these two? Obviously, it is 0.77. Then you take the next number. What is the next number? Minus 0.11. So, we have a max of 0 comma minus 0.11. So, definitely the maximum among these two is 0, that is where 0 is been. Likewise, all the elements from this feature map are passed to a ReLU and we are going to get something like this. So, if you look, if you see here, whatever is the size that we have we had, it is the same size that has been obtained. So, you have nowhere reduced any size. So, with this what you have to understand, ReLU has no role to play in the reduction, or ReLU has no play in extraction. This activation function is mainly used to convert all of the negative values to 0. Let us explore little detail, why it has to do, that we will see in the next. So, if you take an example, see this is one example of x, where if you see all the values what you have substituted here is all 0. If you assume minus 1 as 0, it is all 0 which is being added at the borders, which means you have applied padding. So, there is a padding here, remember. On this input, this is the kernel that you have applied, and this is the feature map that you have extracted. How did we do? This is the output of an conv layer. Now, this is being passed to a ReLU. This is being passed to a ReLU, and this is the output that we have obtained. And if you see here, what is the size of this input? Count from here, it is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It is a size of 7 cross 7. And because you have applied padding, whatever is the size that we have obtained, it is a 7 cross 7 only. So, count it 1, 2, 3, 4, 5, 6, 7, and here it is 7. And because of this, whatever you have obtained, this is also 7 cross 7. 1, 2, 3, 4, 5, 6, 7 and 7 cross 7. So, because you have applied padding, the output of convolution operation is still same as the input, and the output of ReLU is also same as input 7 cross 7. Now, if you apply, this is what you have taken input, you have applied this kernel, you got this feature map, and you got this after passing it to ReLU. Now, for the same input, I will now apply a different kernel. Can you able to see here? There is a difference between this kernel and this kernel. Definitely, whatever the feature map that it is going to get will be different from this. And when that is being passed to a ReLU, we are going to get a different matrix. Similar way, if you take one more kernel, then you will get one more matrix, it is and square matrix, and here also you will get one more feature, after you pass it to ReLU, you will get one more. So, the more such kernels you apply, more such values that you get it, more such matrix of this kind you will be getting. So, let us see with an example here. When you look into this example, this is an input image that is first applied to a kernel, and then when you pass it to a ReLU, this is the output that we are getting. If you change for the same input, if you change the kernel, when you apply it to ReLU, this is the output that we are seeing. So, can you able to see the difference? Can you observe this kernel, just observe only this kernel. This kernel and this kernel, there is a difference, right? One kernel is focusing on horizontal line, one kernel is focusing on vertical lines. So, when you apply different kernel, you are getting a different features that are extracted. So, when you apply this kernel, it is this feature which is being extracted. So, when you see what exactly is the difference, here you are able to eliminate all the features which are not at all contributing for you, which is not very important for prediction. So, all that is been converted to 0. This is what is ReLU, and one of the important component in CNN. So, how do we write this in Keras? Practically, how will we write this? Suppose if you take some image of size 64, 64, 1. So, which means you are considering a dimension 64 height, 64 width, and because you are writing 1, it means it is either a grayscale or a binary. Okay, 3 cross 3 is 3 kernel size 3 cross 3. 32 indicates 32 such different kernels, and at the this convolution conv 2D is an Keras function which is used to perform a convolutional operation, and you should also pass an activation function. And what activation function we are using? We are using a ReLU activation. So, this is the syntax of Keras. We will explore in detail once again in hands on, but this is the line that you will be writing for a convolution operation. Okay. So, before we proceed with further, at this point of time you should know, if you remember, if you recall the concepts of multi-layer perceptron. So, every neuron is connected to every other neuron in the hidden layer. Again, from first hidden layer, every other neurons are connected to every other neurons. So, on each of those connections we had weights, and there is a bias also for every of the layer that we are adding. So, and once you get the output, you will calculate the loss, you will apply optimizers, you will back propagate, and during a back propagation you will update those weights and bias. This is what we have seen in multi-layer perceptron. But when it comes to what we are discussing is CNN here. So, in CNN, what are the learnable parameters here? Though weights and bias, there was learnable parameters in multi-layer perceptron. What are learnable parameters here? Here also we call it as weights and bias only. But what are weights? The weights here are kernels or filters. Now, when we consider a 3 cross 3, we have all, there will be values here. Each of these values is nothing but weights only, and then we have an bias per filter. So, therefore, the learnable parameters in CNN will be once again the weights and the bias. Here the weights are the kernels and then the bias. So, let us see this with an example. So, we know what is the role of a filter. So, filter and kernel are one and the same. We will be often using these words interchangeably. So, when you take a filter, what is the role of a filter? Filter will slide through the entire image and it will extract the features. Now, each filter will have a number inside it, and those numbers we call it as an weights. Now, if you take an filter of size 5 cross 5, and if you have a number of channels as 3, then you know how many number of weights we will have for one filter. It is 70, it is 75. How do you get this 75? It is 5 cross 5 and 3 such filters. Therefore, total weights what we have are 75, and there is an plus 1 bias term that is been added. So, total number of total number of parameters here are 76 parameters. How did we get 76? For a filter it is 75. For every of the filter there is a plus 1 term, that is a bias. So, number of parameters are 76. So, similar way, when you consider a multiple filters, this is one filter. What you are seeing on the left side, this is for one filter. What when there are multiple filters, it is into so many such filters. What we have shown 76 is for one filter. Now, if at all if we have 6 such filters, for example, if you consider an image, input image which will have 3 channels, and you have kernel of 5 cross 5, but there are 3 such channels. Like this you have 6 such filters. So, if you have 6 such filters, then the total number of parameters what we will have here is 76 is for one filter, into 6 we will have totally 456 different parameters or total parameters which the model has to learn here. So, this is a small concept before we actually go into this slide. What is this slide says? This is with the formula, let us see whatever we have seen in the previous, it is the same with the formula. What is the formula here? And if you looked into this, nowhere we have considered the input. We have not bothered about what is the size of the input here. So, all what we have considered is what is the size of the kernel and how many such filters or how many such kernels we are considering. So, the mathematical formula is given by kernel height and width and number of input channels, whether it is an one channel or 3 channels, and then bias term, and NF indicates number of such kernels or number of such filters we are using. Okay. So, let us take with an example. Let us see, we are considering an RGB here where the input size is 32 into 3. Okay. So, here number of channels NC is 3 and how many what is the size of the filter? The size of the filter is 5 cross 5. How many such filters we are considering? We are considering 6 such filters. However, here whatever may be the stride, whatever may be the parameter, it will padding, whether you are using padding or not using padding, that will not have an impact on calculating the number of parameters. So, substitute the values in this. So, what is the kernel filter width and height and width? It is 5 cross 5. Number of such channels here are 3 plus 1 bias. How many such filters we are considering? 6 such filters. So, the size total parameters are 456. So, here is one example. So, if you take the kernel height and width, if you consider, it is 3 cross 3. So, how is that you will be writing? You will be writing it as 3 cross 3 and how many such channels that we have considered? The number of channels here are 3 and plus 1 bias, and how many such filters? The number of filters what we have considered are 64. So, if you calculate, I think it is 1792. I think yeah, this is the values that we are getting it. So, this is the calculation part. Similar way, if you consider this for the second one, we have 5 cross 5, then number of such input channels here is 64 into 64 plus 1, and how many such filters we have considered? 128. So, this is the calculation that we are seeing it. This is important. You will see why all these calculations we need to know. When we are seeing the hands on, you will be able to understand it. Whenever you are proposing your own CNN architecture, when you are coming up with your model, you should be knowing how many such learnable parameters. So, just hold on till hands on, you will be able to understand these parameters. Okay. Let us get into the next part of math, which is we have an RGB image, and that RGB image you have passed as an input, you have performed a convolution operation. What is convolution operation here? You are taking a kernel, you are doing an element wise multiplication and you get a feature map. What will be the output size? That is what we are calculating. What is the formula to calculate? This is the formula that is used to calculate. I is the input minus F is the filter or the kernel plus 2 P. P stands for whether you are applying padding or not applying padding. S stands for whether what is the stride size. So, if you do not specify anything, by default the stride value is 1. plus 1 into D. D here is number of such filters that you have considered. So, let us take this as an let us take one example. So, here the image input size is 32 into 3, which means the height of an image is 32. The width of the image is 32 and the 3 channels indicates it is an RGB image we are considering. Okay. And what is the filter size? The filter size here is 5 cross 5 and definitely how many such channels will be there for a filter? It is into 3. And how many such filters we are considering? The number of filters that we are considering here are 6. 6 such filters we are considering. What is the stride? Stride is 1 and no padding. We are not applying any padding. Then what will be the output size? The minute you see that there is no padding, definitely the feature map that we are getting will be smaller, will be lesser than the input. Can you see here the input size is 32 cross 32, but the output what we got is 28. How did we get this 28? Just substitute the values in this formula. I value of input is 32, filter F is 5, and since there is no padding that is applied, it is 0, stride is 1, this 1. Plus 1. So, we got the value 28. What we have shown here is only for the height. Similar way you will have into the same formula will be repeated in order to calculate the width. So, it is the same formula. So, what is that we are doing? So, when since I have written there, let us not write it here again. So, it is 28. So, 28 cross 28 into what is this D here? D is number of such filters, because for one filter you get 28 cross 28. If you take a second set, you will again get 28 cross 28. If you take 6 such filters, you will get 28 cross 28 into 6. So, in order to understand what exactly we have done here, let us go back to the first slide that we have. Yeah. Can you see here? This is then input image. When you apply the first filter, you got one feature map. When you apply the second filter, you got second feature map. Totally, what is the output? It is a 4 cross 4 into 2. So, if I use the third kernel, definitely you would have got one more feature and you will have into 3. If you use one more kernel, you will have it is into 3. So, overall how is that you will calculate the shape, calculate the size. The size is calculated using this particular formula. So, this is how you will calculate the output. Now, what if you are applying the padding? So, the minute you say padding is applied, definitely the size should be same as input. So, here input is 32, 3 and look at there is a padding that is applied. Because the padding is applied, just substitute the values in this. Can you see the value is retained same as input 32. Since 6 such filters are used, 6 such feature maps are extracted. So, this is how you will calculate the output of a convolution layer. With this, let us now enter into the next component called as a pooling layer. So, what is a pooling layer? How does a pooling layer works? Now, to the pooling layer, what is passed as an input? Can you see? Can you remember what is this? It is an output of ReLU. So, from ReLU, whatever you have got, we have considered that matrix here. So, now whatever is this, now how does the pooling layer works? What is the pooling? So, the very first step for a pooling is it requires an window size. So, the first component you need to define is there is an window size that we need to define. So, for this particular example, the window size that is defined is 2 cross 2. And now once you define a window size, now how many values we are seeing here? We are seeing 4 such different values, 4 values we are seeing this. Once you take a window, what we are going to do? We are performing a summary operation. What is a summary operation? Now out of these 4 values, either I will apply maximum, or I will apply average, or I will apply minimum. Now for example, if I apply max, so what is the maximum among this entire 4 values? The maximum value is 1. Okay. Now what we will do? We will now stride. When we stride it in a pooling, if you do not specify any value for a stride, by default it will take the window size. What is window size here? The window size that you have defined is 2 cross 2. Therefore, the stride by default it will take the value 2, which means it will leave this and then it will go to the next 2 cross 2. What is maximum among this entire? It is 3 and it will go to the next. So what is maximum among this? The maximum is 0.55. Now it will again, so when you move, you do not have any values here. Can you see here? You do not have any values, but if you do not have any values, by default it is 0. So out of this the maximum value is 0.33. Now stride equal to 2. So you will come down, you will take these values. The maximum among this is 0.33 and so on so forth. If you do this, what exactly you are seeing? Earlier the size was 7 cross 7. From 7 cross 7 you have reduced the size, correct? You can see that there is a reduction in the size. Now why is that? So because there is a reduction in the size, pooling we call it as a downsampling technique. What is a pooling in CNN? We know convolution extract the features. What is a pooling? If somebody asks in one word, pooling is, it is a downsampling technique. What is downsampling technique? The input what you passed was 7 cross 7 and what is the output that you are getting? Definitely there is a reduction in the size. Okay, so it is a downsampling technique where you are reducing its width and height. So spatial dimensions are reduced. Okay, so this is what is a pooling. Let us understand what is the role of a pooling here. We have 3 different types of pooling. We have max pooling, we have average pooling, and we have minimum pooling, min pooling. What is a max pooling? When you define a window size, you have some values there. In that, what is the maximum value? That is a max pooling. When you define a window size, you will have some values. In that, if you take an average of all those values, how do you take an average? If you go back to this example, you will take 0.77 plus 0 plus 0 plus 1 and divided by how many such values are there? 4 such values. So divided by 4, that is the average. So we have a max pooling. Here if you see this in this window of 2 cross 2, because the window is defined as a 2 cross 2, you have not explicitly specified about the stride. So stride by default the value is 2. So the next 2 is this, the next window is this, and the next last window is this. So in this the maximum is 9, minimum is 1, and if you take 1 plus 3 plus 2 plus 9 divided by 4, you get 3.75. Then second, in this the maximum value is 2, the minimum value is 1, and when you add all this 2 plus 1 plus 1 plus 2, I mean 2 plus 1 plus 1 plus 1 divided by 4, you get this value. Similar way you will repeat this process. So this is what are the 3 different types of pooling. Now let us see once again with an example here. If you see the window, the size defined here is 2 cross 2, Therefore, the stride is also 2 and the value what we are getting is 1. Then since a stride is 2, you are leaving the 2 columns and then you will take the next. Again this is the window. In this window you apply either max pooling, min pooling or average pooling. Since we are defined it as max pooling, maximum among this entire is 0.33. Again stride 2 and the max pooling you are applying, so 0.55. Again the stride 2, so max pooling is 0.33. Now stride 2 indicates if you are going column wise, you will leave 2 columns. Now you are coming down, so you leave 2 rows and then take the next value. So what is the next matrix? It is this matrix you can able to see, and since we are applying the max pooling, the max among this entire is 0.33, and you will repeat this process completely. You will repeat this entire. Now what exactly is this pooling doing? Now if you go back, what is the original input that we have considered? Let us go back, and then this is the input that we have considered, right? If you look into, let me erase the, if you look into this is the input. What is this input? The input is alphabet X. On this you have applied this kernel, and this is the features that it has extracted, and then you have passed it to ReLU, and this is the output that you have obtained. And if you look into this very carefully, this is an alphabet X. We will say that it is X because you have these, right? Now by applying this kernel, what we have extracted? We have extracted this portion of X. How do we get to know that it has extracted this portion of X? Can you see this value? If you look into this value, you have maximum values here, and if you look into this, nowhere you have disturbed, you have still retained those values. In order to say that it is X, and by applying to this kernel, you have extracted this portion of an X. Similar way, when you apply one more kernel, probably you will extract this portion of an image, and in one more kernel probably you will extract the middle, this portion of an image. By combining all of this, is it not X that we are getting? Right. Now let us go back and then understand what is the pooling layer that has done for us. So now if you see, this is the output, this is the input you are passing it to pooling, and what is this? This is an whatever from ReLU you got, that you are passing it to max pooling. And if you look into this max pooling, observe this very carefully. So we have still retained this portion from the original. So what is max pooling or pooling doing? Now let us go back to the basics again. Input image, input is image here. Image size is too large to pass it to multi-layer perceptron. But otherwise multi-layer perceptron functionality, the way it functions is very nice, but only problem is the size is too large that you are passing, and of course second is spatial information as it is when you pass. Okay. But now what we are aiming here is, I still want to use the fully connected neural network only, but I do not want to pass the complete image. I want to now reduce the size of the image so that you can able to send it to fully connected neural network. Now in order to say it is X, you do not require the complete portion of the image. Even you have downsampled it, right? You have reduced the size. Even by reducing the size, the most important part which says it is X is still retained here. Now what is extracted? This portion is extracted. Now when you have extracted this, I do not require the long part to say it is x. The smaller, most important is also sufficient for me to say it is x. With this, we have now reduced the size. What was your original size? 7 cross 7. From 7 cross 7, when you passed it to convolution by adding a padding, you still had 7 cross 7. That when you passed it to ReLU, you still had 7 cross 7. Nowhere we had reduced the size because the padding is applied. Now by applying it to max pooling, we have reduced the size. In order to identify one person, you do not require the entire image to say that he is so and so or the person is so and so. Some important features are sufficient to say the person. That is what is max pooling doing. Some important which is actually sufficient for our calculation or for our prediction is retained and the rest all are eliminated. So this is what is max pooling. I hope you have understood this. Average pooling will also consider the smaller features, and min pooling will consider only the lowest level features. So practically when you are implementing, we will not use min pooling much. We always go either for average pooling or max pooling. So this is what, how do you write implementation line? What is the syntax for it? What we are applying is a max pooling on a 2-dimensional data, 2D. And what is the size? Compulsory parameter that we need to fix for max for pooling is we need to define the window size. So here the window size is 2 cross 2. If you does not specify the stride, then a stride by default will be 2 here. That 2 is the size of this filter that we have fixed. Do not get confused. When I say filter, filter is not the kernel that we are using. Filter here is this box. So now I want to reduce. So if you want to reduce, how many elements you should consider, from that elements what operation you want to do. So that is the filter what we are talking about. So if you see the Keras implementation, we have written the complete code. Here we have taken the input shape as 28 to 28 to 1, which is an RGB, which is a colored, which is an grayscale, because the channel here is 1, or it can be a binary image. The activation function is a ReLU, 3 cross 3 kernel and 32 such kernels, and the padding equal to same. Because you have written padding equal to same, whatever is the size, the same size will be retained. Okay. When it comes to max pooling, next operation that you are performing is pooling, right. So pooling, max pooling, and you are defining its window size. The window size here, filter window size is 2 cross 2. Now one important aspect, because in convolution you have applied padding equal to same, the correct way of doing is, even in pooling you have to write padding equal to same, because you have applied padding in convolution, right. So you have to apply padding equal to same even for max for a pooling one. This is what I was talking about. The stride will be by default size. No, I want to change the stride. I do not want to have 2 cross 2, the stride as 2. I want to define a stride as 1. Then explicitly you need to define stride equal to 1 cross 1. Explicitly you need to specify. Otherwise, if you do not specify, system model internally will take same as the pool size or the window size. Now, once you performed whatever input is being passed to, the output of this is being passed to pooling. Now, what will be the size of this pooling? How do we define the size of this particular matrix? So it is calculated by this particular formula. So once again you are seeing it is an floor of. So what is the formula here? The formula is, now you see the input what you have passed is, this is the input that we have passed. So this height this width we have to consider. So, input to pooling layer is the output of convolution, which will have the width, which will have the height, and definitely number of such matrices. So, that number of such depends on how many filters you had used. So, it is into D. Okay. So, when you apply, when you take an example, let us take an example, the input is 5 cross 5 and one such channel depth is 1 and filter size, the filter size here is the window size. So, window size is 3 and the stride is 1. So, what is the size that we are going to get? The size that we are going to get is 3 cross 3 and into 1, but since 1 into 1 is just 3 cross 3. How do we get this? So, input here in this formula you apply, it is 5 minus and F is the filter size once again for max pooling, that window size. So, it is 3, stride what we have considered is 1 plus 1. So, 5 minus 3 is 2, 2 plus 1 is 3. This is for height, and the same thing you have to repeat this for the width. Width is 3 into D is number of such. Here depth is only 1. So, it is into 1, which is just 3 cross 3. This is what we have seen. One more example you can see the same we have seen. You can see this, the same what you have in the diagrammatic representation, you can able to see this. We have considered an image of size of 5 cross 5 and then the hyperparameters are these, and then you have got a size as 3 cross 3. Now, what if a padding is applied at an for a convolutional layer? If a padding is applied, what example you have seen now so far, what you have seen is where padding is not applied. Suppose if a padding is applied for a convolution, everything will remain the same, but instead of a floor it is a seal of it. Okay. So, what is seal? The seal is the next highest integer number. So, when floor here is, suppose for some values when you perform this division operation, if you get a fractional number, floor will consider the greatest value less than or equal to this number. For example, we have already seen if it is this or if it is this, you will have a value. But if a padding is applied for a convolutional layer, it becomes a seal of 3.5. What is a seal of 3.5? It is a 4. What is a seal of 3.9? It is a 4. So, this is one important that you need to remember. So, let us quickly recap. We have considered an input. Input is applied to convolutional, ReLU and pooling, and we have applied 3 such kernels. So, this input, when it is applied on this kernel, you will get one matrix. This input, when it is applied on this kernel, you will get one more. Input on this, you will get one more. So, we will get 3 such values, 3 such matrix. So, if you see here, how do you write in an implementation? However, we will be seeing it here. It is 7 cross 7. So, it is 7 cross 7 comma 1 channel, and there is a padding that is applied throughout of this image. Therefore, padding equal to same 3 such filters and of size 3 cross 3 it is applied. And because the padding you have applied at a convolution layer, for max pooling also we will apply the window size here is 2 cross 2 and the padding is the same. Because stride is not specified here, stride by default is 2. Okay. Now, what if you want to apply once again one more set of operations? Once again you are applying convolution, ReLU and pooling. Once again you are doing it, and again you are using 3 different kernels. Then how you are performing? The first kernel will go through this entire 3 images, 3 matrix, and you will perform finally the addition. okay, and the second kernel will be passed through the all these 3 matrix, and you will calculate, you will get 3 such values, you will add it. The third kernel will be passed through all these matrices, you will perform the convolution operation, you get 3 such values, you will add and then you will place it. And we know pooling will reduce the size. Therefore, the end you will see that there is a reduction in the size. Okay. So, now you can ask, why did you do this? Why, what is the importance of doing it? So, that importance you will be able to understand here. Ultimately, the last will be a fully connected neural network. If the last is fully connected neural network, now if you after this, if you apply fully connected, how many such values are there here? There are 4 cross 4, 16. Here we have 16, here we have 16. 48 neurons or 48 features will be passed as an input to an fully connected neural network. For the simple example 7 cross 7, if we are getting 48 for these hyperparameters, if you take a real world example where you are dealing with little larger size image, then you can imagine this size will be very large. So, what we will do? We will apply multiple layers of convolution. Therefore, we have got a smaller size here. Now, what exactly is a fully connected or a flattened layer is, whatever the output we have got at the end of a pooling layer, which will be a 2-dimensional one, that 2-dimensional will be converted into a single dimension, will be converted into a single dimension 1D. How is that will convert? Suppose if this is the output of pooling layer, then your flattened layer will be, this is the flattened layer that we are getting 311 205 143. So, you are going to convert 2-dimensional, which is in 2D, you are converting it into 1D. So, now if you have multiple such, here you have only one feature map. What if you have multiple such feature maps? See, there are 3 such feature maps. So, you will convert the flattened layer as this way, you will convert this. And how do you write the code? You will just call the function flatten. Now, important question is, why to do this? Now, the same example if you take, here if you apply flatten, immediately after this we have 48 neurons, 48 features will go as an input to a fully connected neural network. But once again you have applied the second set of convolution, ReLU and pooling, we have got we have a smaller size. So, how many neurons? It is just only 12. 12 features are being passed as an input. So, you will be able to understand this. Now, can you recall, this is how you were building a multi-layer perceptron, right, multi-layer neural network. So, if you see here after the flatten, if you have 48 neurons, 48 will be passed as an input, then you will have the hidden layer, you will have the next hidden layer, then you will have the output. So, the lesser the number you pass, definitely for this computationally it is less expensive. Why? When more such features, when this value is very high, can you imagine the complexity? One neuron is connected to all other neurons. So, number of weights, biases, of course bias is one for every layer, but number of weights, the computationally it is expensive. So, by applying the second set of convolution, you have reduced the feature map size. If you do it once again, you will further reduce. So, more such layers we will be adding, so that towards the end of the last convolution, last pooling, we will be reducing the size. Why to reduce the size? So that you can pass it to a fully connected neural network. Ultimately, I want to pass it to fully connected. So, this is how. So, once you perform the flatten, so from hands on of multi-layer perceptron, you know, this is the first hidden layer, and this is the output layer. Why output layer? There are 3 neurons, so 3 and activation is softmax. Although there are 2 more hidden layers, we have not included it. I am just showing as an how to do an hands on, how to write the code. Once you write, you will compile the model, and for compiling the model you will calculate the loss, and the loss, because it is a multi-class classification, categorical cross entropy, the optimizer what we are using is Adam. So, what is the role of Adam here? So, once it calculate the loss, you have to reduce the loss. How will you reduce the loss? You will backpropagate, you will update the weights, you will update the bias, and then further if you come back, you have the kernels that are considered for a convolution, you will update those kernel values also. With this we will be achieving getting the lesser loss, and then you will train the model. This is how you will be. And the last concept for this particular session, we have something called as global max pooling and global average pooling. And where do we write this? If you see sometime back when you have applied a flatten layer, the output of pooling layer, can we consider this is the output of a pooling layer? If you have used 4 such filters, we have got this is the for the input. If you have used 4 filters, you are going to get this feature map, this feature map, this feature map, and this feature map, and this is passed to ReLU, you are going to get this. And on all of this, when you apply pooling, you get 4 such. I am not bothered about the dimension here, but I am just giving you what are these 4. So, this is the input, this is the kernels, 4 such kernels, this is the feature map, and then this is ReLU output, and this is pooling output. Now, end of pooling, how many such we got? We got 4. That is what is 1, 2, 3 and 4. We got 4 such. Let the dimension be anything. I am not worried about the dimension. So, we have a certain height and a certain width. Now, what is global max pooling and global average pooling does is, now from this output of pooling what we have got, it is going to convert it into one value. Now, there will be some values here. However, we have an example. Yes, if you consider global average pooling, so what did I tell? It will convert it into only one value. For example, let us assume this is the output of pooling with the first kernel, second kernel, third kernel, fourth kernel. So, this just an example, there are some values here. Now, if the same, if you had to go for flatten layer, what you would have done? It is 3, 1, 1, 3, 2, 5, 0, 2, 1, 4, 2, 1, 4, 7, 2, 4. This is 1. Similar way, second you will continue below. Third you will continue below. So, definitely the size is larger. So, now what you are doing? You are from this entire, when you apply average, take the average of all of these. How will you take an average? 3 plus 1 plus 1 plus 3. You will add all of these divided by number of such values. So, you will get this number. Okay. Similar way, second matrix what you have, add all those values divided by whatever is this size. So, you will get this value, you will get this and you will get this value. What did we do? If you do not apply global average pooling, from this if you want to convert that into flatten, the size is very large. So, instead you can apply global average pooling. If you take a global average pooling, it will just take the average of all the elements. Second, we have something called as global max pooling. In this, what is the maximum value? The maximum value is 7. Similar way, from this second, whatever is the maximum, from the third matrix, whatever is the maximum, place here. So, what exactly is happening here? We are drastically reducing the size of an input feature that we are passing it to an fully connected neural network. However, in the hands on we will be seeing all of this. This is a theoretical concept. So, this is a practical implementation. You can see sometime back here is the place where you had written the flatten layer. After flatten layer you will be applying a fully connected one. So, in the place of flatten layer you can apply global average pooling or global max pooling. We will see this in the hands on. So, with this we have come to an end of this particular session, where in this session we have explored how convolution operation is performed on RGB images, that is a colored image, where we have seen when there are multiple channels, when there are multiple such filters, how convolution operation is performed. So, once the convolution is clear, we then explored the different other layers of CNN. We have seen an ReLU activation, we have seen a pooling, we have seen a flatten layer, and this is required because once you perform flatten, the last requirement is it has to classify. So, for classification we are preparing our data. So, this is the summary. In the next session, in the upcoming session, we will see if at all if there is an overfitting, how do you reduce the overfitting in CNN. We will explore something called as a batch normalization, and then we will have a quick revision of other regularization techniques such as dropout, then early stopping. If at all if there is an L1, L2 regularization, let us do the revision and let us learn in detail of the batch normalization. This is all for this particular session. Till the next session, you can revise. Thank you.